online lecture, the video lecture for these last sections of chapter 2. And again, we had to cancel class this morning, and well, here we go. Here's the class. So I want to go over what we're talking about in section 1.5. And this is unlocking some abilities that are going to help us in algebra, especially situations like this. We're going to encounter this. And according to PEMDAS, our order of operations, we need to do the computation in the parentheses first. Well, that's what we're supposed to do. But there's a problem. If we don't know what x is, how can we add it to 5? Now, x is a number. It's called a variable, and it is a number. It's just we don't know which one yet, and we're trying to figure that out. It's like solving a riddle. So here we're trying to add this number we don't even know to 5. Well, we can't do that, but these parentheses, they're sort of making us do it. So how do we get out of this situation? How do we climb out of this box? And that's what we're going to look at today. So first off, we want to do this. We want to take a look at the commutative property. Now, the idea of the commutative property is the order of the numbers when we do our computation doesn't matter. Now, what I mean by order doesn't matter is when you add two numbers together, you could go 3 plus 5 or 5 plus 3, you're going to get the same answer. It doesn't matter if the 5 is first or the 3 was first. Either way, you're going to get 8. Turns out to be the same with multiplication. 3 times 5 is 15, and 5 times 3 is 15. So with addition and multiplication, these are commutative. So here the order doesn't matter. Now, there are operations that are not commutative. And that's going to be subtraction and division. So 5 minus 3 is 2, and then 3 minus 5 is not 2, it's negative 2, which is a different number. Division, let's say we take 8 divided by 4, we'll get 2. 4 divided by 8, we get 1/2. So the point is, addition, multiplication, you can switch the order around on the numbers. That's fine. Subtraction and division, you can't. So those aren't commutative. The next one's associative. Now for this, the grouping doesn't matter. So for example, and we can think of grouping as associating, like they're coming together. And let's say we have this. 8 plus 4 plus 2, well, that's going to come out to be 14. But instead of grouping 8 and 4, let's group 4 and 2. Well, this will come out to 6, and then 6 plus 8 is still 14. So how we place the parentheses doesn't matter. Then if we do, say, 8 times 4 times 2, well, 8 times 4 is 32, 32 times 2 is 64. But then if we group the 4 and the 2, 4 times 2 is 8, 8 times 8 is 64. So again, the grouping here didn't matter. Now, as you might guess, there are operations that are not associative. And it works like this. Let's say we do this. Well, 8 minus 4 is 4, and then 4 minus 2 is 2. But if we have this, move the parentheses, we'll now associate the 4 and the 2. 4 minus 2 is 2. 8 minus this 2 is 6. So they're not associative. Depending on how you place those parentheses, you're going to get different answers. Division. 8 divided by 4 is 2. This 2 divided by 2 is 1. Or four divided by 2 is 2, and then 8 divided by that 2 is 4. So again, depending on how we place the parentheses, we're going to get a different answer. So again, subtraction and division, they're not going to be associative either, and they're also not commutative. So what good does this do for us? Well, let's go back to our conundrum. Let's say we have something like this. What can we do with this? Well, we're supposed to do the parentheses first. Now, there is something else we could do I didn't mention before, is we have 3 times something. And using the definition of multiplication, we can write that we have 3 of these added together. Now the parentheses are still there. We're still having to compute what's in the parentheses first, and then we can add everything together. So, but by the definition of multiplication, 3 times something means we add that something up. We add 3 of them together. So this is our something. Now here's the thing. Because this is addition, and because addition is commutative and associative, we can drop the parentheses. And then we can associate the x's, because association or grouping doesn't matter. We can associate the 2's. And if you say, well, wait a minute, shouldn't this 2 be added to this before we do anything with these? And it's like, well, again, addition's commutative. Order doesn't matter. So we can group how we want. We can add in whatever order that we want. Again, because of associativity and commutativity of addition. And so we have 3 x's. So that's 3 times x, 3 2's, and 3 times 2. And we've gotten rid of our parentheses. This is great. Now there's a shortcut here. Because doing this every single time is just going to get tiresome. We'll just do this. It's a little way of remembering it. we'll distribute the 3 to the x, distribute the 3 to the 2. This is our shortcut. It's our algorithm. It doesn't make any sense mathematically. It's just a way of remembering that we can go from here to here and cut out all the middle steps. And so we call this distribution. So let me go through an example here. Let's say we're going to do some simplification. So what we do, we just use our shortcut. We'll distribute the 2, and we distribute it as multiplication. We just lost the pin. Pardon me. There it is. We'll get 2 times x plus 2 times 6, or 2x plus 12. And there we go. So that's how we can drop the parentheses, and that's going to be really helpful later on. Now, you might ask, what if you have a minus sign in the parentheses? What do we do there? Well, let's take a look. Let's say we have this. Now we've proven, so to speak, or we see this pattern that we can use when everything's being added. And that's because when we're adding, the order of the numbers or the variables, the grouping of the numbers and the variables, it doesn't matter. But with subtraction, it does. So what do we do here? Well, recall that we can always rewrite subtraction as adding a negative. So now we're adding. And because we're adding, we can distribute. And just for simplicity's sake, adding a negative is the same as subtracting. And there we go. Now again, we want to look for a shortcut here, just to go from here to here, and there is. We can distribute the 3 get 3x minus 3 times 4, or 3x minus 12. So it turns out we do have a shortcut that makes it look like addition and subtraction doesn't matter after all. But really what's happening is the way we came up with a shortcut, we had to convert the subtraction to addition, and then we had to convert it back to subtraction. If we couldn't make this conversion, this wouldn't be possible. But luckily, we get a shortcut that's looks like we can distribute with subtraction with no problems. Let me do an example. So let's say we have something like this. Well, again, we can distribute this 5 to get 5y minus 5 times 3 is 15. And there we go. That's our answer. Now, another thing with distribution, and it has to do with the minus sign. So in math, what you'll see is that we can rewrite x as 1 times x. We do the same thing with minus. If you have a minus x, we can rewrite it as minus 1 times x. Same if you have a number. Any number is a product of 1 with itself. Likewise, you could take a minus number and call it minus 1 times that number. That'll work. And again, negative times positive is negative. So when we distribute, we can rewrite this minus as minus 1 times x plus 2. Distribute the minus 1. And then minus 1 times x, again, we write that as minus x. And then plus minus 2, negative times positive is negative. And then adding a negative is the same as subtraction. So we get our answer. Now, as you might imagine, there's a shortcut here. And what we do is we can take this minus sign and we'll distribute it to the x and to the 2. And we'll treat it like it's the opposite operator. So we'll take the opposite of x, the opposite of 2, because it's a positive 2, so we'll get negative x, negative 2, or subtract 2, and that's your answer. Let me do another example with this. So minus y minus 3. Well, again, we distribute. And what we're going to run into is minus y, and now we have a double negative. Minus 3. Or minus y plus 3. So this minus will become a plus. This positive y becomes a negative y. All right. Now, what's going to become important in algebra later is these special numbers. And these are what you might call your identity properties. And what it says is this: if you add 0 to any number, you just get that same number. So for the number a plus 0, you're going to get a. And again, the order doesn't matter. 0 plus a, you get a. So, for example, if you take negative 3 plus 0, you're going to get negative 3. Or if you had 0 plus negative 3, you get negative 3 also. Again, adding 0 doesn't change anything. Where this is important is later on when we get into algebra, or a little deeper into algebra, what we're going to see, let's say you have 8 equals 5 plus 3. So this is, say, think of this in terms of weights. There's 8 pounds on this side, and there's like an 8-pound weight, and on this side there's a 5-pound weight and a 3-pound weight. So they both balance. But we could subtract 3 pounds from this side. Maybe we chip off a little of this weight and reduce it to a 5-pound weight, which would be kind of difficult, but let's say we got the time to do it. And then we just remove this 3-pound weight. Either way, we're removing 3 pounds from either side. Maybe it's easier to think of these as like sacks of sand. 8-pound sack of sand, 5-pound sack of sand, 3-pound sack of sand. Remove 3 pounds from this big sack of sand, and then the 3-pound sack, we just remove it. So this will now become 5. And we can rewrite this as 5 plus, well, plus, if you have 3, you subtract 3, you get 0 here. 3 minus 3 is 0. And we're going to be doing this a lot in algebra, where we're going to get a 0. These two cancel, as we say. These are going to cancel each other. And then, of course, 5 plus 0, well, that's going to be 5. So this will be very important when we get to algebra. All right. Next is the additive inverse. The idea here, if you take a number and add to it its opposite, you get 0. And we just saw that here. So if you have A, add to that the opposite of A, you're going to get 0. And because this is addition, the order doesn't matter. The opposite of A plus A, you're going to get 0. Let me do some examples here. 3 plus negative 3. You find $3 and then you spend $3. How much is left in your pocket? 0. Or you're short $3, you owe someone $3, and then you find $3, so you can pay him back, and that, instead of being in debt $3, you're brought back up to 0. But when you add something to its opposite, you get 0. And when we talk about cancellation in algebra, this is a key thing. All right. So that's additive. Now this is one, again, it's kind of like, well, why do we bother? All it says is this. Any number times 1, well, it doesn't change that number. Multiplication by 1 doesn't change anything. Or 1 times that number, you get that number. So for example, 3 times 1 is 3, or 1 times 3 is 3. So how does this work for algebra? Well, this is how we're going to use it. Six over 2, or 6 divided by 2, is 3. Now what we could do is we can multiply both sides by 2. And this is 3. Of course, this is 3. So that means this will be 3 times 2, 3 times 2. So what we could do, and you can get a little fancy with this, it may be a little overcomplicated. So bear with me. Call this 2 over 1 times 6 over 2 times 1, because again, we can always multiply something by 1. And then we can do some clever multiplication here. We can call this 1 times 2, or actually, let me not quite make that jump. 2 times 6 over 1 times 2 times 1, 3 times 2. And then, and I'm doing this the way long way, we can say this is 1 times 2 times 6 over 1 equals 3 times 2. 6 over 1 is just 6. 1 times 2 is 2. And then what we end up getting is 1 times 6 equals 3 times 2, or 6 equals 3 times 2. So what's the point of this exercise? What I wanted to do, and I should have mentioned it in the beginning, I wanted to cancel that 2 that was under the 6. The original problem was 6 over 2 is equal to 3. And so the way we do this is we'll say multiply both sides by 2. This is 3, multiply both sides by 2. In algebra, what we're going to do is instead of writing all these ridiculous steps, we're going to take a shortcut. We're just going to say this divides into that, you get 1. And so you get 1 times 6 is equal to 3 times 2. And this is where that multiplicative identity comes in. We've canceled the 2's and we get a 1. And so this is what we're going to get. And what we'll typically do is we'll typically jump down to here. Won't even bother with the times 1. But anyway, that's in the future. So multiplicative identity, though, all we really need to know for now, if you multiply by 1, nothing changes. Multiplicative inverse. So the idea here is this: if you take a number and multiply it by its reciprocal, and again, this is excluding 0, because you can't take the reciprocal of 0. But if you take any other number, you're going to get 1. Or a reciprocal times the number, you're still going to get 1. The reason this is true, let's say you have 2 times its reciprocal, or 1/2. Reciprocal is the flip of a number. You'll get 2 over 1 times 1 over 2. Multiply across, you'll get 2 over 2, or 1. And I should mention that is what a reciprocal is. It's 1 over a. We can think of reciprocals as kind of sort of like opposite numbers, where you have a positive and the opposite of the positive is the negative. The opposite of the negative is the positive. So for multiplication, if you have a, the sort of opposite, though we don't use that word, is 1 over a. And then likewise, the reciprocal of 1 over a is A. If you have something with a 1 on top, well, flip it and the 1 goes away and you're good to go. Let me demonstrate that. So the reciprocal of 3, the way this works is we can write this as 3 over 1. Again, you can always give something a denominator of 1. And then flip it. And that's the reciprocal of 3. These two are reciprocals of each other. Now, if you took 1/2, well, all you got to do is flip it. You'll get 2 over 1, and then 2 divided by 1 is just 2. So those are reciprocals of each other. Now, there's a slightly longer way of writing this. I mean, these two are equal, but just to be consistent with arrows. To go through all the steps on this one, because I mentioned you're going to flip it. Technically, what you can say with 1/2, and then you flip this. 1 divided by 1/2 will give you 2. That's another way of thinking about it, but this works, just as well. Where this part becomes kind of important is if you're dealing with something like this, say 3/4. The reciprocal of 3/4 is 4/3. Just flip it, you get your reciprocal. You can do it this way though. You can say 3/4 is 3/4 over 1, flip it, get 1 over 3/4, and if you do the division, 1 divided by 3/4, you'll get your 4/3. This is the long way of doing it. In actuality, you have your number. If it's a whole number already, think of it as having a 1 underneath it, flip it. If it's already got a 1, flip it, ditch the 1 underneath. If it's a fraction like this, just flip the fraction. And that gives you your reciprocals. And so what you'll get, 3 times 1/3 is the same as 1/3 times 3, and that's equal to 1. 3/4 times 4/3 is the same as 4/3 times 3/4. That's also equal to 1. All right. And again, this will be helpful when we get to equations or solving equations for algebra. So finally, in 1.5, there's what's called the symmetry property. And what this says, A equals B is the same as B equals A. Those are interchangeable statements. In other words, 1 plus 2 equals 3. This is the same as saying 3 is 1 plus 2. You can switch the order around the equal sign, as long as you have the same statement on one side, same statement here. This statement in its entirety gets transferred here. This one in its entirety gets transferred there. And this can be helpful. Good to know. This is the same as, and there we go. All right, so that's really it for section 1.5. If you have any questions, let me know.